Well, how are things
Great. Excellent. Prevnon.
Okay. Well, we have a homework assignment due today. Does everybody wait until 5 o'clock now? Or so you haven't tried the exercises? So.
I have a question.
Oh, you do have a question. Excellent. Leave it to.
I have two questions actually.
All right.
On 12.9, it's one of the ones that's less than or equal to.
Oh, yes. Those are tricky, aren't they?
I'm kind of just confused where I need to put the signs.
Where on 12.9, it's to prove that n squared is less than or equal to 2 to the n. And remember, I had a hint for you on this one. Yeah. You used the result from 12.8 in the proof for 12.9. 12.9, it's to prove that n squared is less than or equal to 2 to the n. Less than or equal to? Less than or equal to. 2 to the n for n greater than or equal to 4. Yeah, now were you able to get 12.8? Okay. Because what you do is in one of the steps for 12.9 you actually use 12.8.
Okay. I mean, I did 12.8.
Okay, all right. So let me give you a hint on 12.9. Okay, so the way you should do 12.9 is this. First of all, I assume that you got the base case all right. Yeah?
It was just the inductive.
Yeah. And so in the inductive case, what is it that you have to prove? You have to prove that what? Because you always have to write out the sentence in the inductive case.
Yeah.
And so what was the sentence that you wrote out?
So it said
Prove
n plus 1
quantity squared
is less than or equal to 2 to the n plus 1.
is less than or equal to 2 to the n plus 1.
Assuming n squared is less than or equal to 2 to the n as the inductive hypothesis.
Yes, that's exactly right. Assuming n squared is less than or equal to 2 to the n as the inductive hypothesis. Now what I recommend that you do here is start with the n plus 1 squared.
I did that.
Okay, and then did you multiply it out?
Yep.
All right, and then don't you see though that you have a
I use the inductive.
and you can use the inductive hypothesis, and so you can say that's less than what? 2 to the, what did you get?
I have 2 to the n plus 2n plus 1.
Yeah.
And then you just say it's less than or equal to 2 to the n.
Yeah, so what you have is you had 2 to the n plus, you had 2 to the n plus 2n plus 1. But this, you can just say, now here's what you're allowed to do. You can say equals, and here for the hint, you can say exercise 12.8. Because that's like a previously proved theorem. Are you with me?
Yeah.
So you can say exercise 12.8.
Would it be equal to, or is it?
No, because what does exercise 12.8 say? What did you prove? Here, let's write out what you proved in exercise 12.8. What did you prove in exercise 12.8?
That 2n plus 1 is less than 2 to the n.
2n plus 1 is less than 2 to the n for what? For what n?
For n is greater than or equal to 3.
For n is greater than or equal to 3. All right? So this is how you would write the hint for that step.
Is it equal to, or is it?
That's why I'm confused.
No. It's, oh, sorry. You're right. This is not equals. Yeah. Oh, yeah. Yeah, you're right.
But is the one before that also the less than or equal to?
Well, what do you think?
Because you're using the inductive.
Yeah.
Okay.
Yeah. Yeah, so this would not be this equals this. This would be this is less than. Right? Now how do you know that you can use this? Because we know that this is valid. When is this valid? For n greater than or equal to what? 3. But what are we doing? Well, if this is true for n greater than or equal to 3, it's true for greater than or equal to 4. Yeah, so it's legal to use this. But this is how you write the hint for that.
And that becomes 2 to the n plus 1?
Yeah.
Well, this is 2 to the n, what will this be? This will be 2 to the n plus what? What will this be? 2 to the n plus 2 to the n. Well, what is 2 to the n plus 2 to the n? What is a plus a? What is x plus x? 2x. So 2 to the n plus 2 to the n is 2 times 2 to the n. And what's 2 times 2 to the n? That's 2 to the 1 times 2 to the n, and 2 to the 1 times 2 to the n is 2 to the
2 to the n plus 1.
n plus 1. You didn't get that? You can review it on the video.
I have another question.
All right. Is everybody clear on this? You other okay. Next question.
The next question is on 12.10.
All right.
You have to make it divisible by 3.
Oh yeah. Yeah. What is the setup on that one? Let's.
Well, from your hints, did you want us to make like a quantification? Or could we do it?
No. Yeah. This is you can do this one a little bit informally.
Because I put it over 3 and this, it has to be equal to 0. Can you do that?
Well. Oh, you know, I had a parentheses around this 12.9 that shouldn't have been there because it was an exercise. But anyway. So in 12.10, you have to prove that 2 to the 2n minus 1 is divisible by 3. Is that right? 2 to the 2n. Is minus 1 down here?
Yeah.
Is divisible by 3 for equal to what?
0.
0?
Greater than or equal to.
Yeah. Okay, so did you get the base case? So here's how to start off the base case. This is what you're trying to prove. And I think instead of writing this formally with, there exists a k, blah, 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 let's just write this out in English. So here's how you do the base case. Here's how you'd set up the base case. So base case, you would say 2 to the, you actually write this out in English. This is a little strange. 2 to the 2n minus 1 is divisible by 3. Now, do you agree that this is a proposition?
Yes.
It's a statement that's either true or false. Yeah. So we say, so this equals by the base case, and what's base case?
0.
All right. And then each step it's being written out.
Okay, so at the end.
So in the end, you're going to say 0 is divisible by 3, and we know that's true. Boom.
Okay. So is that the only way that you could do it?
Well, this is our way to. How did you do it?
I did 2 to the 2n minus 1, and then I put it over, and I said divided by 3 has to equal 0. And then you don't have to.
No. Is divisible by 3 does not mean divided by 3 equals anything.
If it equals 0, that means divided by 3.
You would
No, I don't think.
If you divide by 3 and there's nothing left over, then...
But if you would have to say mod 3 equals 0.
Yeah.
Yeah, and you said divided by. Are you with me? So mod. It has to be mod. Yeah, Alex?
Yeah, say equal 3n.
It's kind of a cool thing though, that you can mod.
Is there a mod symbol? You can't use it.
Well, in C++, the mod symbol is this. And in GCL, it's MOD. You write out
So
MOD.
Is divisible by 3, you could say mod 3 equals 0.
You could say mod 3 equals 0. Okay, so you write this out. Okay, so now let's set up. So this is dot dot dot. Now, how would you do the induction case?
2 to the 0.
No, I mean, because, you know, here, you must prove. Must prove.
So if you just have 0 is divisible by 3, you can just stop there.
Yeah, because because 0 is divisible by 3, and that's true, yeah. I mean, does everybody agree that 0 is divisible by 3? Little shaky on that?
I didn't think it was supposed to be.
Yeah, it's divisible by,
0 divided by 3 is 0.
yeah. 0 is,
3 is 0.
0 is divisible by 3.
It just seems kind of weird though.
Well, 3 is divisible by 3. Why is 12 divisible by 3? Because wait, why is 12 divisible by 3? Because 12 divided by 3 is 4, remainder 0. Remainder 0. Why is 9 divisible by 3? Because 9 divided by 3, yeah. Because 9 divided by 3 is 3, remainder 0. Why is 0 divisible by 3? 0, remainder 0. Remainder 0. So why not? Yeah, mod. Yeah. Okay, but now here's what I want to make sure that we get this next one. With the induction case, what do you have to write down? Must prove, but what must you prove? 2 to the what?
2 parentheses
2 parentheses
n
n plus 1 minus 1. There's more. Is divisible by 3. That's part of the. Are you with me? Using, yeah, or assuming that what?
That is
2 to the 2n minus 1, what? Is divisible by 3 as the what?
inductive hypothesis.
As the inductive hypothesis. Now let me get you started on this. After you write that out, so must prove, blah, blah, blah. You can write that out. And then here's what I recommend you do. What I recommend you do is you start with this 2 to the 2n plus 2 to the 2n plus 1 minus 1 and do some arithmetic on it. All right? And so but then when you get to the end, you're going to have to do some English on it because we're not doing the whole thing. You
So
see
when
what-
you put in the inductive hypothesis, are you just going to say true?
Well, start with this. Start with 2 to the 2n plus 1 minus 1. Start with this, yeah? And then do some math on it.
Do you have to say is divisible by 3?
No. What I'm saying is get this. Here's what you should do. In order to use the inductive hypothesis on this, you need to get this to where part of it is what you have for the inductive hypothesis.
Right.
Can you do that?
Just split up the 2.
Yeah, this 2 to the 2n plus 1 is 2 to the 2n times 2 to the 2. And what is 2? All right, are you ready for this? Here comes the little rabbit out of a hat. Ready for a little rabbit? What is 2 to the 2?
4.
What's another way to write 4? What's another way? 4 to the 1 is one way, but what's another way?
2 times 2.
What's another way?
8 divided by 4.
Those are all true, but they're still not useful. What's another way? What's another way to write 4? Did you hear that? Another way to write 4 is another way to write 4 is 3 plus 1.
So you could say
So by math.
Etc. Boom, boom.
And once you get to that, that 4 there, write that 4 as parentheses 3 plus 1. And then multiply that out. Are you with me?
Multiply that by 2 to the 2n.
But yes. Yeah. Are you with me?
I don't understand how can you use the inductive hypothesis?
Well, okay, now I'm getting to that. So basically what do you wind up with? Tell me after you do that what you wind up with.
2 to the 2n, parentheses, 3 plus 1, and then minus 1.
Yeah, multiply out distribute the parentheses.
Okay.
So then what do you have?
I have 6 to the 2n.
No, not 6.
3 times
3 times, because it's 2 to the 2n. Ooh, little algebra.
So 3 times 2 to the 2n plus
Plus-
2 to the 2n minus 1.
Yes, that's your goal here. Now you have to make some English arguments. Now, did you see the hint that I gave you on the webpage?
Yeah, I just didn't know how to apply it.
Well, now you were going to apply it.
Because now I have my inductive hypothesis.
Yeah, so now what do you know? What do you know is,
That we know that that last part is divisible by 3.
which part?
So we have to prove that
The
6
2
to
to
the
the
2n.
Now we just make an English argument. The rest of the proof is in English.
If 2 to the 2n minus 1 is divisible by 3.
Yes, okay, you know that. You know that you know that.
And we know that 2 multiples of 3 add together to become divisible by 3.
Is divisible by 3.
Prove that 6 to the 2n is divisible by 3.
Yeah, and so, but we already know that 2 to the 2n is divisible by, we know that 3 times 2
Multiplying
times
it by 3 makes it still divisible.
divisible by 3, and then if you add two numbers that are divisible by 3, you know that's what? So therefore the whole thing is divisible by 3.
I don't really know how to write it.
Well, you have to write it in English. You have to write what we just said.
So I could write 3 times 2 to the 2n just by itself because we've already proved that the other part is divisible by 3.
Yeah, you explain each part, you explain why each part is divisible by 3, and from that, you know that the whole thing is divisible by 3. You have to explain that in English. See, you guys, unfortunately, I've trained you so much. Yeah, we've been trained so much to be formal methods that when we get to these informal parts of our proofs, there's resistance to having to, how do I prove this? Well, you got to start writing some, it's like the coin problem that we did last time, right? You have to,
Wait. 2 to the 2n minus 1 is divisible by 3.
and how do we know that? 2 to the 2n minus 1, how do we know that's divisible by 3?
Inductive hypothesis.
Yeah, we know that because of the inductive hypothesis. Now, what else do we know?
6 to the 2n is not 3 times 2 to the 2n minus 1.
I know, but how do we, but on the other hand, whatever n, I mean, we know that, we don't know that 2 to the 2n is divisible by 3, but we do know that 3 times that is divisible, because we do know that 2 to the 2n is an integer, right?
Yeah, right.
We know that 2 to the 2n is an integer, so if 3 times an integer is divisible by 3.
Sure.
Are you with me? So we can make that claim easily. Right? Because
So when we invoke the inductive hypothesis, does that part just go away? 'Cause-
there's no more math to do, there's just English to do. So nothing is going
You
away.
don't write it in hands, you just write it out.
You just write it out. Yeah, you have to you write out the logic.
That's why I was so confused.
Yeah. No. You don't say equals by this, equals by this. At this point, you have to make a logical argument at the end.
Okay.
Yeah, this is always, whenever we start doing word problems like this and having to use, it's always, people are always resistant to that because we're kind of like machines now. Equals, boom, 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 formally, but now we got to do some informal stuff. And of course, in a math class, it's exactly the other way around. Everything is informal. So this is the way you have to prove stuff, and if you were taking a math class, this is how they prove stuff in math. You got to write all this English out and say, well, this is, and we know because of this, and so therefore, da-da-da. Okay, are we good? Well, it's good. So you guys have tried, you guys did try your homework, so you did have questions. So that's really good for the people watching the video. I'm sure they will.
And people in the future.
Yeah, and people in the future, right? So this is for posterity. All right. Okay, now the next thing we're going to do is, have you guys heard of Fibonacci numbers? Okay, so here's how it works. Here's how Fibonacci numbers work. F sub 0 is 0, and F sub 1 is 1. So these are the first two Fibonacci numbers. The sequence starts with 0, 1. Now, and so it sounds like you've heard this before. 0 plus 1 is what? 1. 1 plus 1 is what? 1 plus 2 is what? 3. 2 plus 3 is 5. 3 plus 5 is 8. And 5 plus 8 is 13, right? And then etc., right? So, so these numbers are denoted f sub 1, f sub 2, f sub 3, f sub 4, sub 5, sub 6, sub 7, etc. Right? And it turns out, I think this describes a population growth. I seem to remember an example once of rabbits. You know how rabbits multiply, and if you wait a generation and you have so many rabbits here, then however many appear in the next generation depends on how many were in the previous generation. And there's some. I think there's some. Well, I mean, I think this is a model for population growth.
Stuff in nature.
But it happens not only that, there's also this thing called the Fibonacci, there's a spiral that's based on this Fibonacci thing. Now here's another place where these numbers actually crop up. Now let me ask you a question. I'm going to draw a rectangle.
Okay. I won't stop you.
There's a rectangle. What do you think about that rectangle? Do you like it?
No.
Why not?
Lateral.
It's bad. It's like
Well, I mean, assuming the lines were straight. I mean, do you like it?
No, it's too thin.
Yeah, it's too thin, right? Well, okay, so how about this?
That's a square.
Yeah. I mean, that's kind of, and how about this one? So how about this one? Do you like this rectangle?
What is the point of this?
Well, I'm just asking how you like it. I'm just asking how you feel about this. How you feel about it. I mean, do you like them?
No.
Well, I mean, tell me, what is the most pleasing, Doesn't that just do your heart good? I mean, don't you like this one better than these? Don't these kind of seem like too skinny, too...
The sum of the two ends should be the length of one side.
Yeah. So the Greeks had this idea. They said, what is the most pleasing to the eye? Actually, now in modern, in modern days now, this is the aspect ratio of a display. I mean, so, do you want widescreen display? Do you want old-fashioned televisions that had square, or do you want, So the Greeks had an idea. They said, well, what is the most pleasing, how do you draw a rectangle that's the most pleasing to the eye? And you know what the rule was? The rule was, if you take this rectangle that is the most pleasing to the eye, the characteristic that it should have is this. If you make a line here, such that this left part of the rectangle is a square, so if you take this length and you come over here and you draw this, then this rectangle that's left over should have the same ratio, should be the same pleasing to the eye as the whole thing. Do you see what I mean? In other words, this one should also, if we took this and looked at it, this way, it should also have this nice pleasing ratio.
The exact same ratio?
Yeah. In other words, this leftover rectangle should be the same ratio, aspect ratio. Yeah. Yes. Yeah. Okay. So here's how it. So here's what we're saying. What we're saying is, if this distance from here to here is a, are you with me? And therefore this is a, right? Because we're making this the square. So if this is a, all right, and then if we call this one b, from here to here, okay, then by definition of this pleasing ratio, what should be, so here, if we do this, then by definition, by definition, what should we have? We should have A is to what? B. So we should have A is to B as what?
A plus B is to A.
As A plus B is to A. Yeah? As A plus B is to A. Now, does everybody see how that worked by that definition? Okay. But now let's do a little arithmetic math on this. So this A is to B as, now does everybody agree that I can make this A over A plus B over A, but A over A is 1, so this is 1 plus B over A. And now does everybody agree that we can do A over B is 1 plus 1 over A over B, right? Just taking the B to the denominator. Are we good with that?
Yeah.
Now this ratio A is to B, that's called the golden ratio, all right? So the golden ratio this one that is pleasing to the eye. The golden ratio is, we use a letter for this in math, we use the letter phi, is phi equals, and that's this ratio, A over B, right? So now in terms of phi, what is that equation? What is that? In terms of phi, so instead
1
of,
plus 1 over phi.
so, and what equals 1 plus 1 over phi?
Phi.
Okay, so we have phi equals 1 plus 1 over phi. Are you with me? Okay, now let's multiply both. Let's solve this for phi. Let's multiply both sides by phi. What do we get?
T squared.
We get phi squared equals what?
Phi plus 1.
Phi plus 1. So let's take this to the other side, and what do we get? Phi squared minus phi.
Plus 1. Or minus
Oh, sorry. Oh, yeah, minus phi minus 1, yeah. Minus phi minus 1 equals 0. How do we solve a quadratic equation? Can we factor this?
Phi minus 1.
Okay, let's do the quadratic formula.
I think we're going to have to use the quadratic formula.
So,
So what do we have? So now let me see. What is that? It's minus, what is it? Minus, how does that, what's the quadratic formula? Minus b, minus,
so it's 1.
okay, so phi equals minus b, what's b?
1. Negative 1, sorry. But
Minus, okay, so minus b
plus or minus.
plus or minus the what?
It's supposed to be just
The what? Square root of
B
B squared.
b squared, so that's
1.
minus 1 squared, b squared, minus
4.
4
AC.
1.
times, a is
1 negative 1.
4, a, c is what?
Negative 1.
Negative 1
All over 2A.
all over
2 times 1.
2 times 1. Is everybody good?
Does it simplify to that?
Well, let's see. Let's see. So now so we have phi is minus 1, negative minus 1 is what? 1, right?
Yeah.
Plus or minus the square root of minus 1 squared is what? 1. Negative 4 times negative 1 is
Plus 4.
positive 4, plus 1 is 5. So this is 1 plus or minus the square root of 5 over 2. So there's 2 roots to phi, right? So here's what we say. So here's what we're going to do from now on. From now on, phi is going to be 1 plus the square root of 5 over 2. And then phi hat is the other solution. Is going to be 1 minus the square root of 5 over 2. All right? Now, somebody have a calculator? Nobody has a calculator? Well, what's the square root of 5? Roughly. 2 point
1, 3.
something.
It's not pretty.
Yeah, it's some. Oh, you have a calculator. Okay, so 2, and then 1 plus that is 3.23, and divide that by 2.
1.8.
So there's your ratio. So phi is approximately equal to what?
1.618.
1.618 ... It goes on forever. So there's your ratio, the pleasing ratio, about 1 to 1.6. Okay? And now, you guys, if you look on your equation sheet, let's take a look. The definition of the Fibonacci number is f sub 0 is 0, f sub 1 is 1, and f sub n is what? F sub, the one before it, plus the one before that. Now, are you ready for this? Do you remember whenever we said, up until now, all of the proof by mathematical inductions that we've done, we've always had one base case, right? But do you remember when we were doing this here? Yeah, so now, but do you remember that in general, it's not just the previous one implies this, it's the previous one and the one before that implies this. Or maybe this one and the one before that and the one before that. So now we're in a situation where we see that in this 12.5 for our working one, we're not just going to use the previous one, we have to use the previous one and the one before that, because there's two base cases. Because each one doesn't depend on just the previous one, it depends on the previous one and the one that went before. In general, you could define some wacky sequence of numbers by one that depends on, actually you could do, I wonder what that sequence would be. If it was 0, I mean, no, if it was, 0, and then the one was the sum of the previous one and the one before and the one before that. Then you'd have to have 3 base cases, and then it would do something. By the way, this sequence is so amazing, and it occurs so much, and there's so much mathematical theory behind it. There is actually a Fibonacci association.
No, yeah, I met someone who was obsessed with it.
Oh, really? Yeah, people do get obsessed with it. It's,
like the most attractive people in the world have the exact Fibonacci.
see, with their face, their facial features, yeah. And there's a quarterly journal, and it's still being published today. I knew that there was one, many years ago, but I checked it out just before class, and they're still publishing. There's a quarterly journal that comes out of mathematicians, and their whole career, is all they do is they study the Fibonacci sequence. This Fibonacci. There's a huge amount of mathematical theory behind it. Yeah, and there's really beautiful pictures. If you look up on the web, you can see the shell. You can see there's the the nautilus. What happens is, see, now if you do the same thing here, so then if you do the same thing here, then this has that ratio. And then if you do, so what happens is, if you do a spiral, if you do a spiral like this, and then this spiral's like this, and then if you do this one here, then this spiral's like this. And so there's a Fibonacci spiral that is, in fact, the way the nautilus shells are shaped. So it happens in nature. And if you look at the seeds and flowers, if you take a look at a sunflower and you look at the seed, it occurs there. It's really quite fascinating. All right. So let's take a look at a couple of these theorems, and we'll see. And there are some equalities and there are some inequalities. Okay, so 12.14.1 is the definition of the golden ratio, and that's this phi is 1 plus the square root of 5 over 2, and phi hat is 1 minus the square root of 5 over 2. And in 12.15 we have some easy equalities that are easy to prove. Let's just prove 12.15 really quickly. This is just math. So let's I'm sorry, say it again.
We already had that in the steps to figure out the golden ratio.
What, that phi squared? Oh, you're right. Phi squared. Oh, we just did it. Yeah. Because that's how we got. Yeah. We did that. Yeah, you're right. Well, actually, we could plug it in to see if it's. We could. What we would be doing is we'd be plugging it in to see if that's true. In other words, what we have is phi squared. What we have is phi squared equals phi plus 1, just to check our work.
Math.
Yeah, well, let's do it. This is 1 plus the square root of 5. This would be,
Are we starting with the whole thing?
I'm just, yeah, we're starting with, starting with the whole thing. So this is 1 plus the square root of 5 over 2 squared equals, well, here, let's just do the one side. This is 1 plus the square root of 5 over 2 would equal, what would this be? 1 plus, here, yeah, actually this would be 1 plus the square root of 5 squared over 4, right? Is that right?
Yeah.
And then this would be 1 plus
It's
2 root 5 plus 5 over 4. And this would be, okay, so this would be 6,
3 plus rad 5 over 2.
yes, 3 plus rad 5 over 2. Is this going to work?
Close.
We have to get this to be phi plus 1,
Oh, that's
right?
it. We're done.
That
Yeah,
is it.
it shouldn't be a 3. You did it wrong.
That's it. No, that's
Right.
it.
No, this is right. This is right because
If V is
Just
1,
break-
yeah, this is 1 plus, this is, this 3 is,
2 plus
is 2 plus 1 root plus,
Yeah.
no, 3 plus 1 plus root 3, yeah, it's
2 plus 1.
2 plus 1
Plus root
plus root 5 over 2, which is 1 plus
1 rad 5.
1 plus root 5 over 2, which is 1 plus phi. Anyway, well, whatever. You're right. That was a little pointless.
Do it that way.
Well,
Could
whatever.
have took the whole thing.
Could have taken, yeah. Well, but like you say, we did it before.
and then 3 steps.
Yeah, okay. But anyway, so actually 12.4. But now, the interesting one, though, is 12.16, right? Let's prove 12.16. Because what is 12.16? It is an inequality. And now what we're going to do is we're going to use what technique? Proof by?
Induction.
Mathematical induction. Yeah. So let's prove 12.16. Prove 12.16, and which is that f sub n is less than or equal to phi to the n minus 1 for n greater than or equal to 1. So base case. So what should we write down first? This, okay? So f sub n is less than or equal to phi to the n minus 1 equals by, what's always our first reason? Base case. And we know from here that n is 1. That's given. So what are we saying here? F sub what? 1 is less than or equal to phi to the what? 1 minus 1. Is everybody good?
that's the 1.
Okay, and we know this equals by, we know that f sub 1 equals what?
1
Equals 1 by definition.
in math.
By definition. And also by math, we know that 1 minus 1 is 0. Anything to the 0 is 1. So what do we have? 1 is what? Less than or equal to 1. Is that true?
Yep.
That's true. Boom. Are we good?
Induction.
No.
Base case number 2.
Yeah. This is base case n equals 1. Now what?
Base case n equals 0.
Base, no.
Equals,
2.
Is everybody clear on this? See, we want it to be for 1, 2, 3 times. So we have to do the base case for 1 and 2. Is everybody with me? 2 base cases now. So here, base case.
How do we know we have to have 2 base cases?
Because whenever we do, because
Just because.
it depends on the 2 that went before. See, whenever we do it for in general, we will assume that, we will assume that that is true for n, assuming the one that's before and assuming the one before that. So we're also going to have, in our induction case, we're going to have two inductive hypotheses, not one inductive hypothesis. Are you with me? So similarly for the base case. So here's the base case n equals 1. Here's another base case. So we have to do two base cases. So now what do we do? So now what do we start with? F sub n is less than or equal to what? Phi to the n minus 1. So this equals by what? Base case n equals 2. Is everybody clear on this? And why 1 and 2? Because each one depends on the one before and the one before that. And the first one here is we're proving it is for 1. So we've got to do it for 1 and 2. Yeah?
Yeah.
Okay, so base case n equals 2 says what?
How do you know that
F sub
there's
two.
going to be two base cases?
Because the Fibonacci sequence is defined, because each one is dependent on the one before that and the one before that.
Just because you know Fibonacci is
Yes,
two.
Fibonacci
yes.
requires two.
Fibonacci requires 2. If we,
Yeah,
So
Okay.
anytime we're using f sub n, we need to do 2.
yes, yes. And there could be one where it requires 3. I mean, if there was a different sequence. If I gave you made up some sequence on the exam and said F0 and F1 and F2 is this, then you'd have to have 3 base. Okay? So now what with this? So what is this? F what?
2.
Yeah, F sub 2 is less than or equal to phi to the what?
Minus 1.
To 2 minus 1. All right? So now what do we do? Okay? So this equals by definition of F sub 2 and math. So what is that? So what is F sub 2? So this is 2 is what? No. F sub 2 is not 2.
F sub 2 is 1.
F sub 2 is 1.
He was like 1.6 something, right?
Yeah. So this is 1 is less than or equal to what?
Phi.
To phi. But this equals by definition of phi.
1 plus radical
1 is less than or equal to, what did you say it was? 1.618 ... which is true. 1 is less than or equal to 1.6. Yeah? Okay, now what about the induction case? Now what do we have to write down? Yeah, but now prove prove that F sub. Now, there's several different ways to do this. We can either do F sub n, or no, I guess I'm sorry, there's,
One way to do it.
yeah, okay. So what do we have to prove? F sub what? N,
F sub
n plus 1. Prove F sub n plus 1 is what? Less than or equal to phi to the n plus 1 minus 1. To make it, to really make it clear, you should do it like this. N plus 1 minus 1 like this, right? Because it's n plus 1, you see the n plus 1 here, you see the n plus 1 here. But now what do we assume?
A lot.
No, not a lot. Well, how many? 2. So now what do we assume? Assuming what? Now what's the one before this?
N.
Yeah, so assuming what? F sub n is what? Less than or equal to what? Phi to the n minus 1. And what's the one before that? F sub n minus 1 is what? Less than or equal to what? Phi to the, phi to the n minus 1 minus 1. As the what? Yes, as the inductive.
But what if n is 1 and you have f sub 0, which is 0? F sub 0, 0.
Well, we're doing this in the general case. We're starting with the 0. I mean,
If sub 0 is 0,
They're asking us to, they're asking it for n greater than or equal to 1.
Right.
Okay? So now what should we, now tell me, what is it that we're trying to prove? Which one?
The top.
This one. So should we start with the left side or start with the right side?
The left side.
You're right. I think we should start with the left because then we can expand it out, okay? So let's start with, so we'll start with f sub n plus 1. Now watch this. F sub n plus 1 equals by what?
12.4.
Yes, by definition.
12.14, my bad.
Yeah, definition 12.14. What?
F sub n
F,
minus 1.
F sub
F sub n minus 1 plus F sub n
F sub n
plus F sub n
plus F sub n minus 1. Now, is everybody clear on that? Right? Because by definition, each one, this is, it's actually 12.4 with n replaced by n plus 1. But, yeah?
Yeah.
Are we good? So, but now what do we know?
We can, there, this is less than or equal
This is less than or equal to by the what?
by the induction case.
By the inductive hypotheses. By the so because we know that f sub n is less than or equal to what?
Phi to the n minus 1.
Phi to the n minus 1. And we know that f sub n is less than or equal to what?
Phi to the n minus 1 minus 1.
Phi to the n minus 2. Yeah? Are we good? Almost there. Now comes a trick. Now comes the big trick. What are we trying to get this to? What are we trying, look, what are we trying to get this to? Yeah, phi to the n. Now, so why would you do what I'm about to do?
Split the 1 in the end and the 2 in the end.
We're going to factor out. We're going to factor out a phi squared. Sorry, phi to the n minus 2. But here's what we're going to do. Which one of these is bigger?
Phi to the n minus 1.
Yeah. We're going to factor out the smaller one.
Right, which you did.
So here's what we're going to do. We're going to say this is phi to the n minus 2 times the quantity. Now,
Phi plus 1. Wait,
Isn't there an easy way to do this?
no, this is the easy way to do it.
Phi plus 1, right? Yeah.
Does everybody see that? You're right, it is phi plus 1. Yeah?
Yeah.
Are we good? Because after all, I mean, how can you verify this? Phi to the n minus 2 times phi is phi to the n minus 1, and phi to the n minus 2 is it. And the reason we're factoring out phi to the n minus 2 is so that we can get this phi plus 1. Because, sports fans, if we look up here, what do we know about 12.15?
Phi plus 1 is phi squared.
Yes.
Nice.
So this equals by 12.15
Wow.
phi to the n minus 2 times what?
Phi squared.
Phi squared. And phi to the n minus 2 times phi squared is what?
Phi to the n.
Equals, by math,
So wild.
phi to the n. And another way to write phi to the n is phi to the n plus 1 minus 1. Boom, we're done.
Wow. Never would have gotten that.
That's not going to be on the test.
What do you think?
You bet.
And what do you think you're going to do for homework?
There's no way.
And what do you think you're going to do for homework?
12, 16.
Yeah, maybe, you know. Yeah? Does it sound good?
Sounds great.
So, 0, 1, 1, 3, 5, 8, 13.
Whoa.
Hi.
I thought you were talking binary. I was like, please stop.